Hello, welcome to Chem Camp. I'm Mrs. Newman, and I'm here to discuss the 2023 AP Chem free response questions. So we've officially reached the point in the school year where the AP Chem test has been taken, and the College Board has released one version of the 2023 FRQs. However, scoring the exam is going to take a little bit of time, and they will not release the scoring guidelines until after grades have been given. So I figured I'd go through these problems and show you how I would go about answering them and give you my best guesstimate as to the point distribution for each one. Now, I have no insider information. I'm just going to share a little bit of information with you based on several years of experience working with AP Chem students, this content, and the College Board questions. So let's do a little bit of chemistry. The very first free response question of 2023 starts by stating, answer the following questions related to manganese compounds. And in part A, they say manganese has several common oxidation states, which is true of your transition metals, which Mn is. In part A, they ask you to write the complete electron configuration for an Mn atom in the ground state. Since they're asking for an atom, that means that since Mn has 25 protons in its nucleus, it should have 25 electrons in its electron configuration. Not only that, but they should all be in the lowest possible energy levels since they're asking about the ground state. So this is just a normal electron configuration. So for Mn, that would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then be very careful. It should finish with 3d5, keeping in mind that your d orbitals will always fill one energy level less than the prior energy level for your s sublevel. Now this would be the complete configuration, and this is what you should definitely earn a point for in this part of the problem. The big question is going to be, well, what about the shorthand or the noble gas configuration? So you could write a noble gas configuration for an atom by taking the noble gas prior to it in the periodic table. In this case, it would be argon, so we would write Ar in square brackets, and then finish with 4s2, 3d5. Now, whether they're going to give you any points for this shorthand or not is going to be up to the College Board, and we'll probably find out when the score guides come out. Part 2 states, when manganese forms cations, electrons are lost from which subshell first? Identify both the number and letter associated with the subshell. So they make this one a little more complicated by pulling a transition metal. What you have to keep in mind is that your electrons are always going to be lost from the valence shell first. Now, by definition, your valence shell is the energy level that's the outermost or highest energy level of that atom. So here, although the 3 Ds fill after the 4 S's, that 4S is going to be your valence shell, and the electrons from that subshell will be lost first. Now, manganese can also lose electrons from that 3D, which is why it could gain an oxidation state all the way up to a +7. Interesting. The problem continues by stating that a student performs an experiment to produce a manganese salt of unknown composition, MnXCl aqueous, and determine its empirical formula. The student places a sample of Mn solid in the beaker containing excess HCl aqueous, as represented by the following equation, and they give you the chemical reaction that's going to occur. And then they state that the student heats the resulting mixture until only MnXCl solid remains in the beaker. The data are given in the following table. and they give you the mass of an empty beaker, they give you the mass of the beaker and the Mn solid, and they give you the mass of the beaker and MnXCl(Y) after heating to a constant mass. In part B, they state calculate the mass of Cl in the sample of MnXCl(Y) solid remaining in the beaker. So, in order to do that, we got to take our data and perform some calculations. The very first thing I'm going to do is actually subtract the mass of the beaker from the second measurement given. So 61.262 minus 60.169 will actually give us 1.093 grams of just Mn. I'm going to do the same thing to that next measurement. Subtract the mass of the beaker. So taking 62.673 minus 60.169 gives us 2.504 grams of the MnXCl(Y). The reason why we need these values is because the difference between them will actually give us the mass of Cl. So 2.504 grams minus 1.093 grams gives us 1.411 grams of Cl. This work with the answer and the unit, don't forget your units, should also earn you a point on this exam. Now, this is the proper way to do this, or the proper etiquette, by subtracting the mass of the beaker. You could have also simply taken the 62.673 grams and subtracted from it the 61.262 grams, since this all should have happened in the same beaker. And you should still get the same value of 1.411 grams of Cl. Let's continue working the problem. Part C asks you to calculate the number of moles of Cl in the sample of MnXCl(Y) solid remaining in the beaker. Well, I have to find moles, but in part B, I actually found grams. So I'm going to pull that answer down, the 1.411 grams of Cl, and I'm going to convert that to moles of Cl. I'm going to bring grams of Cl to the bottom of my stoich ratio to cancel, and from grams of Cl, I can always go to moles of Cl using the molar mass. Since there's just one atom of Cl here, it's going to be 1 times that 35.45 to calculate the molar mass. So 35.45 is going to go on the bottom, 1 mole up top, and that means I'm going to take 1.411 and divide it by the 35.45. Should get you 0.03980 in the calculator, which rounded to proper sig fig should be 0.0398 moles of Cl. And you should earn a point for this part of the problem. In part D, they state that the student determines that 0.0199 moles of Mn was used in the experiment. Use the data to determine the empirical formula of MnXCl(Y) solid. Well, for empirical formula, usually I first need to know the grams of each atom. We had the grams of Cl, and then we need to know the moles of each atom. We figured out the moles of Cl, and they've given us the moles of Mn, which means we have to divide each one of those numbers of moles by the smallest quantity. So I'm going to take 0.0199 moles of Mn and divide it by 0.0199 moles, since that's smaller than 0.398. That should give me 1 Mn atom And I'm going to do the same thing for Cl. I'm going to take 0.0398 moles of Cl and divide it by the 0.0199 moles. And that should give me 2 atoms of Cl. So the empirical formula for this compound should be MnCl2. If you're able to complete that section of this free response, you should also pick up a point. When we get to part E, they tell us the student repeats the experiment using the same amounts of Mn and HCl and notices that some of the MnXCl splatters out of the beaker. Very important there. As it's heated to dryness. Will the number of moles of Cl calculated for this trial be greater than, less than, or equal to the number calculated in part C? Justify your answer. So again, big key. If some of that MnXCly splatters out of that beaker, then you've lost some of that mass. So if some of the MnXCly is lost due to splatters, then the mass of the beaker and the MnXCly will be lower, causing the calculated mass of Cl to also be lower. If the number of grams of Cl calculated is lower, then the number of moles of Cl is also going to be lower. So resulting in a calculated number of moles that will be less than the number calculated in part C. For this particular question, not only are you going to have the correct answer, but you're also going to have the proper justification to get your point. Let's keep going. So we've made it to the final letter, letter F, but they've made it 4 parts, so let's keep chugging along. Not only did they make it 4 parts, but they also switched topics on us here. They went from a very stoichiometry-based problem to now a little bit of electrochem. So let's read what they wrote. Another compound of manganese, MnO2, is used in alkaline batteries, represented by the following diagram. Some half reactions are given in the table. So they give us a diagram of the battery, and they give us a table of half reactions, and they're all reduction half reactions, meaning that the species in the reactant is actually gaining electrons. And for part 1, they say, based on the half reactions given in the table, write the balanced net ionic equation for the reaction that has the greatest thermodynamic favorability. 3 very important words here. The thermodynamic favorability is actually referring to a negative delta G naught or a positive E naught. And the greatest means we're going to be looking for the largest value of either of those. Now, since our table gives us reduction half reactions, it also gives us the standard reduction potential listed there, or the E naughts. So we're going to focus in on E naught here. Now, if I take a look, there's only one half reaction that has the MnO2 in it. And it, at the moment, has it as a reduction half reaction with the highest cell potential of 0.15 volts. So we're going to keep that one as a reduction and look to switch one of the other two half reactions so that it's an oxidation half reaction. For a galvanic cell, which this battery is going to be, if we want thermodynamic favorability, you need one reduction, one oxidation half reaction. So I'm going to take a look here, and I have a cell potential of negative 0.76 for the Zn2 plus gaining 2 electrons, and I have a cell potential of negative 1.28 for the ZnO solid gaining 2 electrons. Well, if I flip these two reactions, then I have to change the sign to that cell potential. So I'm actually going to change the arrow of that second half reaction. I'm going to flip it and have it run in reverse. So now it's an oxidation half reaction. And as soon as I flip it, I also change the sign of that cell potential. And the reason why I selected that one is because then it'll give me the greatest E naught for the overall cell, whereas flipping the negative 0.15 volts wouldn't give me the greatest. Now, as soon as I flip that arrow and I have one oxidation and one reduction half reaction, then I can actually work on adding these two equations together to get my net ionic equation, keeping in mind that a species that appears on the reactant side of one of those reactions will cancel with the same species on the opposite side of the other reaction. So for instance, here in the bottom half reaction, I've got 2 moles of electrons that are actually going to cancel with 2 moles of electrons on the product side of that top half reaction. Same with water. I have 1 mole of water as a reactant in the bottom half reaction, and that's going to cancel with 1 mole of water in the top half reaction. Finally, I have 2 moles of OH minus that are now on the reactant side of that top half reaction, and that's going to cancel with the 2 moles of OH minus on the product side of the bottom half reaction, which means I can now carefully put these two half reactions together to get my net ionic equation, where I've got Zn solid plus 2 moles of magnesium oxide, MnO2 solid, yielding 1 mole of zinc oxide, ZnO solid, plus 1 mole of manganese oxide, Mn2O3 solid. Now, if you were able to put down that entire net ionic equation, hopefully you'll be able to be getting a point from the College Board for it. For F Part 2, they ask you to calculate the value of E naught cell for the overall reaction. Well, since we had to figure out which one was going to be our oxidation half reaction based on the reduction half reaction potentials, all we have to do to find E naught cell is add this potentials together. So we're going to add positive 1.28 volts for that oxidation half reaction plus 0.15 volts for the reduction. So 1.28 plus 0.15 should give you 1.43 volts. And I believe the College Board will give you another point for that answer with the work and the unit. In F Part 3, they ask us to calculate the value of delta G naught in kilojoules per mole. So for this part, we get to use one of my favorite little equations, delta G naught equals negative Nifty. In other words, delta G equals negative N for the number of moles of electrons transferred, times F, your Faraday's constant, times E naught, or your cell potential, for the reaction. So for this particular reaction, our delta G naught is going to be negative. If you recall from our equations, we transferred 2 moles of electrons. So we're going to fill in 2 moles of electrons here, times Faraday's constant from your reference sheet. So 96,485 coulombs for every 1 mole of electrons, times your cell potential that you calculated in part 2. So the 1.43 volts. Except a volt is actually a joule per coulomb. So if we plug this into our calculator, don't forget the negative sign, -2 times 96,485 times 1.43. That gives us negative 275,947, which rounds to negative 276,000 joules. We can't leave that as our answer though, because they actually asked us for our answer in kilojoules per mole of reaction. So we're going to take the negative 276,000 joules and convert it to kilojoules. So there's 1,000 joules for every 1 kilojoule. So we're talking negative 276 kilojoules for every 1 mole of reaction. This part should also gain you a point if done correctly. F part 4, the final part to this FRQ, states that a student claims the total mass of an alkaline battery decreases as the battery operates because the anode loses mass. Do you agree with the student's claim? Justify your answer. I'm going to go ahead and disagree. It is true that as a battery or a galvanic cell operates, the anode does lose mass. But as that happens, the cathode actually gains mass. This is going to cause the total mass of the battery to actually remain the same in accordance with the law of conservation of mass. So here you should wind up earning a point for the correct answer and the justification. Once again, these answers are just how I would go about answering these questions. The scoring guidelines have not been released at the making of this video, as well as the point distribution. It's just my best guess at how they might assign the 10 points that are usually allotted to a long free response. If you have any questions, leave them in the comments. If I've made a mistake, because I am only human, also leave that mention in the comments as well. If not, continue to follow along for more AP Chem content. Be well.